Thanks for clicking over this video. If you wanted to learn PDN analysis using Altium Designer, then this is the correct video you have clicked on. Now on level 3 part 1 we have discussed power budget for a complex board in very detail. If you haven't watched that video, then click over the I button and it will direct you to that video. Now in this video we're going to understand the net-wise block diagram which will create from power budget and schematic of our project. After that we'll put all these information from power budget and net-wise block to PDN Analyzer tool, and then we will go for the simulation. After simulation we'll analyze the results, and if there will be any issue or any fails will be there, we'll implement those changes back to design, and we'll keep doing that. It's a simple loop process. If we'll keep doing that until all the test cases will pass. People who don't know which tool I'm using, it is Altium Designer 22.1, and if you wanted to get the free trial of that tool, I have put link in the description. You have to just click there and register yourself. Within 24 hours you'll get the license. PDN Analyzer tool is a separate license from Altium Designer, so for that I have put a separate link. For purchasing PDN tool license, you have to click over that link. With that said, let's roll the intro. So here I have created a net-wise block diagram from power budget and schematic design. People who don't know how to create net-wise block, then you have to visit earlier levels. There I have discussed it in very detail. But here I just want to brief you. So how I have created this. So here I have mentioned all the blocks with its net and its designator. So for example, here I am using a JST connector which is our power input, and I have named it J3 because this is our designator for JST connector. And what is the net on the pin 1, which is 12 volt underscore in, and another net is ground. So this is how we basically mention the designator and nets for all the blocks we are using on our power budget, which will be helpful when we're putting all this information on PDN tool. So let's open Altium Designer. So this is the board that we are going to simulate for power distribution network, and if you'll see the schematic, here we are using 3 motors. I just wanted to brief you before going further. And this is our power input and current sensor block. So here we are using a power input which is J3, and that is going to another voltage regulator which is responsible for 5 volt output. And here we have a current sensor which is we are using for 12 volt input, and again we have a MOSFET and current sense register that is connected to the sensor. Alright, so this is this I've mentioned and discussed in very detail on part 1 of level 3. Let's move to the simulation part. Firstly, go to the tool PDN Analyzer. Now here we have to enter all the nets and their voltage values. So voltage values, so by default it's automatically picked some nominal voltages using their net name, but we have separately calculated the voltage on each and every net. For example, from our power budget, if you can able to see, for plus 12 volt underscore in, the calculated voltage is 15.10. So this is the voltage we're going to fill on PDN tool. So let's start with 12 volt. On 12 volt net, the voltage is 12.21. So here we'll enter 12.21 and we'll select that and add to the currently identified DC nets. Now another net is 12 volt underscore in. So let's see what is the voltage of 12 volt underscore in, which is 15.8. So we'll fill 15.8 here instead of 12 volt and we'll include it. 5 volt is fine, we're going to use it as it is. Let's see what else we need to include. Another net we need to include is in underscore 2 plus, and here the voltage is 12.385. So we have to find that net, which will be in underscore 2 plus. Let's see, here it is, 12.385, add selected, Now let's see what else we need to include. 12 we have already included. Another net we need to include is net C34_1, which is again an input power net for 7805. So, and on that the voltage will be exactly same as 12_in, which is 15.8. So C34_1, we have to find that net C34_1, and it will be 15.8. Add selected. Now another net we need to include, don't forget to add ground. That is very important net. Alright, so we have added 5 volt. Here we don't need to add any net because one component will be, so here PDN tool will imagine the connection between LED and this resistor, right? So we have to enter one net which will be 5 volt and another net will be ground. I'll show you how it will happen. So this is done. This connection is fine. Now here we need to include this connection as well. So on this, for MOSFET, which is Q1, so as I told you on part 1, only one motor at a time will going to run for this circuit. This is the purpose of this whole design. We're not going to run all the motors simultaneously because that will be very huge current, right? So this board was nothing, just a test jig that I've created to test few motor drivers. Alright, so here, okay, so here for this 12 volt load, we have MOSFET and ground. So here also we don't need anything, any special net to add there. Alright, so these are all the nets we're going to add. Press OK now. Now as I told you, we have to compact this setup. So for compacting the layout, you have to go to File and left click over Compact Layout. Alright, now before going further, I'm just going to save it, and this will be our level 3. Alright, so you can name the simulation as well if you want. Now firstly we're going to add nets here, so I'll double click on this one, select ground, press OK. I'll double click on this one, select 12 volt in, OK. Now from where this 12 volt is coming from, so for that I have to right click on this wire and you have to add source. What type of source is there? So in our case we have normal voltage source, which is 12 volt in and ground, and that is coming through J3 GST connector. What is the voltage on that? I've already told you. Now you should know what is the maximum amount of current your source can provide. So I know in my case it is 5 amps. Press OK. Now another step is we have to add series elements. So from block diagram, we got to know between 12 volt in and 12 volt, we have two components. One is MOSFET, another is a sense resistor. So we have to add those. And their designator is Q4 and R68. So that's how I always create netwise block. If I'll put all this information here, then it will be like so messy. Alright. So we have to add series component. For that we have to right click here and left click over extend net. Now what is the series net you wanted it to extend? So in our case, firstly it will extend to in_2+. So I'll select that, press OK. Now we have a series element. What is the series element here? That is a MOSFET. So I'll double click on that. Here you have to add the information. What is that series element? So in our case it is Q4. Now here you have to put the information. So from MOSFET datasheet you can able to get what is the amount of resistance it has or RDS on, that you can put here. So I've already noted down that is 80 milliohm. So I'll go there and put 80 small m. Now here you have to enter maximum current. So I know the maximum current we're going to use through MOSFET is 3.5 amps and our MOSFET is rated for more than that, right? If you want, you can put that information from datasheet. And if you are sure, you don't need to put that, because if it is high, then you don't need to worry about that. Now press OK. So here we have added a series element. Now we have another series element, which is a 5 milliohm resistor. So I'll go back there, extend net, and that will be extended to plus 12 volt. Double click on that. It's a 5 milliohm resistor and its designator is R68. So I'll put that value. Now here you have to enter what is the amount of current it can handle. So in our case it is don't care, because that is how we select the component. Alright. So these things are done. Now we have to add load, because we have reached here, right? So the first load is 7805, which is directly on plus 12 volt underscore in. So for that, what we have to do, we'll just right click here, add load. What is that load? So what type of load you wanted to add? Either it is IC, register, linear, SMPS sense, right? So in our case it is LDO that we're going to use. What is the input of that LDO? It is plus 12 underscore in, right? And where that plus 12 volt underscore in is going, it is going to R61. That you will got to know from schematic. What is the output? It's 5 volt. And from where it is coming from? It is coming from U4 and ground is U4. Now here you have to select what is the V out. So in our case V out is 5 volt. R out, these are all information we don't need to fill here, because we have already considered voltage drop and all those things. Now maximum current is important and power dissipation is important, that you can get from the data sheet, or current consumption requirement. Alright, so we have connected a load. Now we have another load, which is our motor driver. So for that we have to add another load, and that will be IC. Alright, what is that IC? Q1, and its ground is connected through R14. So we have to find R14 here. Now what is the load current? It is 3.5 amps. Minimum voltage, maximum voltage requirement for that. If it is required, you can put that, or if it is not required, then you don't need to put it. So in our case it is don't care, because we know what is the amount of current, or sorry, what is the amount of voltage that is going on MOSFET, right? And it is more than that, so we are fine with it. Now press OK here. This is our block diagram. Now further on this regulator, we have to connect some load. So to extend the regulator, because here voltage regulator is acting as a load for this source. Now further on this voltage regulator, we have to connect few things. So for that, right click here and add VRM to new network. So now our voltage regulator will be a source, and we have to add loads here. Add load, and first we'll add resistive load, which is a normal 1K resistor connected to LED. So for that we have to, what resistor which is connected to 5 volt and which LED which is connected to ground. So it is DS10. Alright, now here you have to enter resistance. In our case it is 1K, and if there is any voltage limit, then you can consider it here. If not, then it's okay. Now we have to enter another load, that is MUX. So MUX comes under IC. It is not a resistive load. So 5 volt is connected to a ferrite bead, which is FB6, and ground is connected to MUX, which is U6. What is the load current? We'll got to know from the power budget. So it is 50 milliamps. Let's add that. What is the voltage requirement? If you have any, you can enter it. Now we have to add another load, which is current sensor. That is again a IC, which is connected to FB4, and ground is connected through current sensor, which is U5. What is the load current on that? That we have mentioned here. It's 0.1 milliamps. It's very small, but still we are considering it. Alright, so we have connected everything. Let's save the PDN Analyzer circuit and analyze the network. Congrats, we have passed all the tests. Now we have to see if anything is critical on our layout. Now let's analyze the result and put it on our report. So for that we'll just go to the visual tab here. Now, so this is for now we are just analyzing this 5 volt network. And firstly you have to click over highlight peak values. And for voltage we'll look for minima. So there we wanted to see where is maximum voltage drop, right? So maximum will be the maximum voltage and minima will be the voltage after drop. And here we'll get the value. So as you can see, the maximum value for the voltage is 5 volt, right? Which is we are getting here, all right? And the maximum voltage is, sorry, the minimum voltage is also 5 volt. So let's see on our scale. If your scale is showing some 0 to 100%, you have to just select displayed. So here you can see we are not seeing any voltage drop. Voltage is very regular, which is 5 volt. Let's see the current density on this network. So firstly we'll see what is the maximum current density. So maximum current density is on this line, all right, and which is 6.57 milliamps per mm square, which is really less. But still, if you wanted to capture and discuss it, I've already told you how to capture this thing. And here you can see the ground as well. Ground plane is pretty much okay, right? So for ground plane, here you will get the maximum. Okay, so this is 24.3 amps per mm square. All right, so this is something, I guess, some layer change which is happening here, and that is happening through single or couple of VRs or something. All right, so for that what we will do, so we got a point which we need to consider for current density, and we have to change it if something is wrong in our layout. If you want, you can select it 3D and see if there is any via or not. So for that you have to hold shift key, and using that you can rotate it. So it is on top layer only. As you can see, there is no via. Still, okay, there are a couple of vias, so it may be happening due to vias only. All right, we'll see that. So let's make it like that. Go to the 2D mode. We'll just go here and select image capture, and here we'll fill a screenshot. This is what I do, underscore the density of current, which is 24.3 amps per mm square, and save changes, done. So this is we have included on our report. Now if you wanted to see, similarly as I told you, if you wanted to see the second maximum of current density, you can see it is nearby. Third maximum is also nearby. Okay, so this is particular area you have to look into in your design, what is wrong with that. Similarly, for minimum it is fine, it is really less, it's almost 0 amps per mm square, right? And voltage we have already verified. The maximum is 5 volt, minimum is 1.98 millivolt, which is on ground. All right, so this is also something strange you have to look into. So I'll capture that as well. And this is 03. for voltage, and here we'll see the voltage is 98 millivolt. So just look into that, what is that voltage. Obviously it's not dangerous or it will cause any problem in your design, but yeah, why this small amount of voltage is there on your ground plane? So you have to find that. All right, let's move to our first network. All right, so this is our first network. We'll go to visual. Firstly, we'll look for voltage. So maximum voltage is 15.8, which is okay, and minimum voltage is 15.3, which is here. So there's 0.5 volt drop. Why this is happening, you have to find out. So I'll capture that image as well, and here the voltage is 15.3, or you can say 15.3 from 15.8. all right, save changes, done. Okay, now we'll see current density. So current density minimum is 0, obviously. Maximum we have to look into in the same section where voltage is dropping. So obviously these current and voltage are correlated here. So as expected, the current density is very high, which is 122 amps per mm square. So we have to look into that as well. Done. These are the probably two things we found here. Let's check into ground plane. So I'm just closing all other. Firstly, look for voltage. Is there any voltage on ground plane? So the maximum voltage on ground plane, which is 5.14 millivolt. So we have to see why this is there. So let's capture image. Ground voltage is 5.14 millivolt. Save changes, done. Just check for minimum. Minimum is fine. Current density on the same area, it is really huge. So if you remember from our another network, we are getting the maximum current density on the same area for 5 volt network. So this is the same thing we are getting here as well. So we are not capturing. If we'll solve there, it will be automatically reflected here as well. So yeah, these are the information we have to look into, and we have to find what are the problems. Apart from that, these are all the information you will get on your report. So let's generate report. For that, we'll go to visual, click over report. Okay, so we want both of the networks, all the images, generate report. Alright, report is ready. Let's double click on that one. So I just wanted to see all the images are included or not. So these are artwork. Okay, this is our network. Okay, these are the images that we have captured. Right. So this is the voltage drop from 15.8 to 5.3. This is high current density on that MOSFET, and this is on ground plane. Alright, these are other waveforms that we have captured, sorry, other screenshot that we have captured. Apart from that, lot of other information that is obviously useful. One more thing I wanted to tell you, so before simulating for PDN analysis, I just wanted to make sure your stack up is correct, because this is how PDN works. It just take all the information from your stack up, generate ODB++ file, and put that on PDN tool, and using that it got to know like what are the geometry of your or what are the thickness, dielectric material, and all the things you are using on your PCB design. Accordingly, it just generate all these results. So make sure if it is correct in your design. So this is our level 3. In level 4, we'll go for more complex block diagram, we'll go for more complex simulation, and that's it. Let me know in case of any doubt in comment section.